okay? And without further ado, I would like to introduce Daniel Rakita, right? Daniel is a PhD student of computer science at the University of Wisconsin-Madison. Very interestingly, Daniel took a bachelor in music performance, right, from the Indiana University Jacobs School of Music, which is a very interesting beginning of career path. And then from music, he went to computer vision, then to animation. And from animation, it was just a small step to robotics and robotic movement planning and execution, right? So his research lies basically in the intersection of these things, like motion planning, trajectory optimization, shared control, and human-robot interaction. So whenever you're ready, Daniel, take it away.
Awesome. So I'll share my screen. All right. So hopefully this is working for everybody. I can start the presentation. All right. Is this good to go? All right. So thanks so much for the introduction and thanks for inviting me. And before I get started, I just wanted to give a big shout out to the organizers of this whole talk series. I think it's so great that despite everything going on in the world, the organizers put together this really nice platform so we as a community can still come together and synthesize and share ideas like this. So a big thank you to them. And yeah, if just a heads up, if my connection starts to go out throughout the talk, just, you know, shout out at any time, let me know, or like, if you have any questions, definitely feel free to chime in at any time. All right, so jumping right in here. So the majority of my PhD work has been dedicated to coming up with algorithms that allow robot manipulators to effectively move in the world around us. And I think this begs the question of what does effective motion really mean in a robotics context? I think it could mean a lot of different things in a lot of different domains and applications. But throughout this talk, I'll argue that there are three important factors when considering robot motion generation. And to give a sense of these three factors in action, I'll use the following example. Say the Sawyer robot here has to get the cup from the top shelf to the bottom shelf. So I think we all have a sense that any definition of effective motion should include the notion of feasibility, meaning the robot motion should be smooth, continuous, and avoid colliding with the environment. And just to give a side-by-side comparison here, I think it's clear that the feasible motion on the right is more effective than the infeasible motion on the left. But what if instead of moving a single cup, the robot now has to move this stack of 2 cups from the top shelf to the bottom shelf? If we use the same feasible motion as before, this is no longer effective motion in this case, since the top cup will fall to the floor. So in this example, while the motion is feasible, it's still not effective, since in some sense the motion lacks accuracy. So to create an effective motion in this case, we need something to generate motion like the one on the right here, that is both feasible and accurate in the sense that the robot maintains an upright end effector throughout the motion. And taking this example one step further, let's say we now want to allow the individual on the left to control the robot platform using our motion control algorithms to move the stack of cups, maybe using some sort of shared control interface. In this case, just having feasible and accurate motion won't be effective if it means that it takes many seconds or even minutes to compute these motions. Thus, the motion on the right here is more effective in this case because it is feasible, accurate, and was also computed fast enough to keep up with real-time interactive demands of the task. And to be clear here, by fast versus slow computation, I'm not really referring to implementation quality, although that does play some role in some cases. I'm referring more to the fact that some problems themselves in robot motion generation may be inherently complex, say NP hard or exponential in nature. So we have to get a bit creative to come up with solutions quickly. So to quickly recap here, the three factors of effective motion that I've brought up so far are feasibility, accuracy, and computation speed. And I really think of these three things as kind of vertices for my particular research space. And different algorithms have different trade-offs in this space. And I'll keep coming back to this illustration throughout the talk to point out where I think current algorithms kind of lie in this space. And of course, I think the goal that everybody is aiming for will be a general algorithm that would hit kind of all of this triangle. And I don't think it's too controversial of a statement to say that no one has really achieved an algorithm that does all three of these things. But a lot of my work has been spent kind of chasing this overall goal. And I'll point out throughout the talk where I think we are in terms of achieving it. So here's an overview for the rest of my talk. I'll spend some time talking about the technical methods that we've come up with for achieving accurate and feasible robot arm motion in real time. I'll highlight some application spaces where we have applied our technical methods. I'll touch on some ongoing and future research threads and end with a brief discussion before the Q&A session. So jumping into the technical methods. So the primary motion framework that I'll be discussing for achieving accurate and feasible robot arm motion in real time is called RelaxedIK, which we presented at RSS in 2018. Our method matches a series of end-effector pose goals in Cartesian space as best as possible without sacrificing motion feasibility. In contrast, a direct IK solver like TrackIK seen here exhibits infeasible motion qualities such as self-collisions, kinematic singularities, and joint space discontinuities. On the other hand, something like real-time motion planning approaches do provide motion feasibility guarantees. However, they often require long sweeping motions that sacrifice end-effector pose accuracy in order to achieve these guarantees. For example, this motion shows the robot moving along this long arcing motion just to go a short distance in end-effector space to avoid a self-collision. So our method not only exhibits feasible motions that avoid self-collisions, kinematic singularities, and joint space discontinuities, but it also exhibits accurate motion that consistently matches end-effector pose goals over time. And coming back to our triangle view of this research space, while TrackIK has motion accuracy and computation speed, it lacks motion feasibility. And real-time motion planning has feasibility guarantees, but lacks motion accuracy, and it's relatively slow to compute solutions on the fly. RelaxedIK tries to gain a better mix of these three factors by relaxing a bit of motion accuracy to gain a lot in motion feasibility. So how do we achieve this under the hood? We achieve many objectives on the fly by casting the standard IK formulation as a weighted sum nonlinear optimization problem, where motion objectives such as end-effector pose matching, smooth motion, self-collision avoidance, and so on are encoded as individual terms in the sum. We present a normalization procedure such that our method is able to effectively make trade-offs between many potentially competing objectives. The weighted sum objective function and a set of constraints are provided to a nonlinear optimization solver at each update, where a new robot configuration is calculated. So for details on all the objectives and constraints that we include in the solver, please see the paper. But in this particular talk, I'm just going to highlight how we formulate the self-collision avoidance term. So our collision avoidance term is trying to achieve two high-level goals. First, estimate a distance to a collision state in order to maximize this distance at each optimization. And second, we want to calculate this distance as fast as possible such that this procedure is amenable for a real-time optimization control loop. So to achieve these goals, we first approximate the robot's geometry with shape primitives and line segments and perform distance checking between all pairs of links. So this procedure does work and it is robust, but it is too slow for real-time use. So our central idea here is that we can sample hundreds of thousands of instances of this original collision potential function and train a neural network to approximate that function instead. So the output of this neural network function reliably resembles the output of the original function, but it's 2 orders of magnitude faster just to do a feed-forward pass through the neural network, making it plenty fast enough to serve as a single term in our optimization framework. So we evaluated RelaxedIK against alternative motion synthesis approaches on 7 robot platforms, ranging from 5 degrees of freedom to 8 degrees of freedom on 5 separate tasks. And we tried a couple of instances of RelaxedIK in our evaluation, one designed to be more accurate and the other designed to exhibit more motion feasibility. And we found that both of these versions of RelaxedIK outperform TrackIK and real-time motion planning in terms of accuracy, motion feasibility, and motion smoothness across all robots and tasks. We offer an open source version of RelaxedIK if anybody wants to try it out or extend it. We are also actively developing on top of this framework, and we'll continue to kind of announce on those developments on the GitHub page. So definitely check out there for all the updates. I'm also kind of implementing a brand new version of it. I think with each implementation, it gets further from prototype research code to more thought out, more organized, kind of ready to go production level code. So we're excited about the development and where we can go with all this. All right, so now that we have RelaxedIK as an initial method for achieving feasible and accurate motion in real time, what can we actually do with it? So the next part of the talk, I'll be talking about how we've used RelaxedIK in other research areas, mostly in teleoperation and shared control. So the first method I'll talk about is called mimicry control. And this is work that we presented at HRI in 2017. And this is pretty much exactly what it sounds like. This is a teleoperation interface that where the user demonstrates a motion in free space with their own arm and hand. And the robot attempts to mimic the motion as best as possible so that it can accomplish tasks in the same way. And this is what the end result looks like here on a real robot. So the user just has a motion controller in their hand, and they're demonstrating how the robot should execute this Tinker Toys task with their own hand. And here's another example where the user is folding a shirt. So again, a pretty dexterous task that would be pretty difficult to do with another interface without directly kind of demonstrating to the robot how to do it. So one thing that is probably pretty evident just by looking at this problem is that a robot arm and a human arm can be very different. They can have different geometry. The robot may move much slower or faster than a human arm. The robot may be larger or smaller than a human arm. And even the number of degrees of freedom could be different. For example, the UR5 here has 6 degrees of freedom where a human arm has 7. So to overcome these differences, here's an overview of one way to solve this problem. We can capture a position and orientation of the user's hand, say with a motion controller. This gets mapped and scaled to the robot's end-effector space. And using inverse kinematics, we can solve for the robot's joint values corresponding to the end-effector pose goal. And this whole process can repeat at each update in the control loop. So way back in 2016 and into 2017, we tried this method in some preliminary work and pilot studies, and we used some standard inverse kinematic solvers, and here's what we got. So many standard IK solvers across the board were not really up for this task, either due to convergence failures, discontinuous jumps, motion inaccuracy, kinematic singularities, and so on. So looking back at our overall approach, based on our preliminary results, it was clear that this last step here at the IK stage needed to be more robust. And we kind of developed RelaxedIK in parallel with this work, and it ended up being just perfect for this motion retargeting problem, as the smooth, feasible, and accurate motions provided by the solver afforded a really nice and immersive experience for the operator. And we ran a user study with 24 novice participants between the ages of 18 and 46. And we compared 3 control interfaces. So we had our mimicry control, 6 degree of freedom stylus device, and the native touchscreen interface of the UR5 robot. And all participants tried out all control interfaces, so this was a fully within user study. And we tested all these interfaces on 3 home care tasks. And briefly looking at our results here, so looking at the results from the 3 tasks and kind of the objective time results from those, we see that mimicry control scored significantly better, reducing each task time by anywhere from 1 to 3 minutes on average over the 6 degree of freedom stylus device and the touchscreen interface. And looking at training task time, we were able to, our participants were able to complete the training task much faster using mimicry control than the other interfaces. In fact, if we look at even the 3rd training task trial using the 6 degree of freedom stylus device, this was still considerably slower than even the 1st trial for mimicry control. So I feel like this was really tapping into some intuitive sense of how to complete tasks and transferring that directly to the robot. So when reflecting on the feedback we got during our mimicry control evaluation, we noticed that we consistently got one particular kind of comment. So we often heard like, the control method was easier to use and more natural than the alternatives, but it was still difficult to clearly see what the robot was doing. And when we went back and looked at what was happening, we often saw situations like this, where even though the user was standing right behind the robot, they had to consistently shift their viewpoint back and forth just to see what was going on. And when thinking about this problem, we thought, if this is such a big problem when the user is literally standing 6 to 10 feet behind the robot in the same room, this problem will just compound if someone was actually doing remote teleoperation from the other side of the world. So we thought this visibility problem in telemanipulation was something we should really start thinking about. So to solve this, we looked at a solution where there's an automatic dynamic camera that can move the viewpoint and come up with a sufficient viewpoint on the fly for an operator. And this is work that we presented at HRI in 2018. So this is the endpoint we'll be working up to in this work. So we have a user remotely controlling a robot arm. And on the left, we see what the user is seeing on screen. And on the right, we can see what is actually going on in the remote environment. We have a second camera and hand robot arm alongside the manipulation arm that is automatically and continuously servoing in real time to provide a sufficient viewpoint of the remote environment. So there are really 2 halves of this problem. The first being the control of the manipulation robot using a motion controller. And the second being the camera robot intelligently moving to provide a viewpoint that it estimates will best support effective manipulation for the user. So the first half of this problem, consisting of remapping the user's motion to a robot arm in real time, still uses the same mimicry control interface that I mentioned before. So for this part of the talk, I'm just going to highlight the second part of the problem, which is the moving of the camera to provide a sufficient viewpoint. So the big problem we were looking at is when faced with this kind of viewpoint that is clearly not sufficient to manipulate something in the environment, what should we do? So our main premise is that the camera should move on the fly in order to dynamically adapt and optimize the viewpoint to select effective viewpoints for the remote operator. And looking back at our solution, the automatic dynamic camera method provides solutions for a lot of the problems that may come up from alternative approaches, such as an end-effector camera or an array of static cameras, such as avoiding occlusions by manipulation or by the manipulation arm, avoiding occlusions by the grasped object, avoiding disorienting views. We can tailor the control frame to how the user is seeing things on screen. And we can afford context and detailed views based on how close or far the camera is from the manipulation point. So it's clear that the camera robot is going to have to consider many potentially competing objectives on the fly, such as the ones listed here. And to account for all of these objectives in real time, we organize these terms to form components of an optimization. And if we kind of squint as the components come into focus here, you notice we get the exact same RelaxedIK kind of formulation that I discussed before. And the really nice thing about the RelaxedIK framework is it's very flexible and it can accommodate a variety of nonlinear objective terms. So we can even include other things related to just camera motion and cinematography in the optimization, such as always looking at the target point, the look at target, avoiding camera rolls, which will be really disorienting, avoiding occlusions caused by the manipulation robot, as well as favoring views from above for certain situations like a tabletop environment. And lastly, we can automatically decide on the distance that the camera will be from the manipulation point to afford either context or detailed view of the remote environment. So briefly going over our evaluation of this approach, we again had a within participants study with 24 participants where we compared our automatic camera method to an array of static cameras and an end-effector camera. And we hypothesized that our automatic dynamic camera would allow participants to complete more subtasks, and it would also be perceived as easier to use and more fluent. So looking at our results, we see that our automatic dynamic camera method led to improved performance scores over the alternative approaches, and was also perceived as more fluent and easier to use over the alternative approaches as well. And we also extended this method in work we presented at RSS in 2019, where the camera robot was able to adapt its motion based on some understanding of the environment, as well as some shared control feedback from the operator. So in this example, the operator is actually able to see into the drawer in order to get something out with the improved viewpoint. So the last RelaxedIK application I'll discuss in this talk is a bimanual shared control method that was published in Science Robotics in 2019. And this is work that was done in collaboration with Laura Hyatt at the Naval Research Lab. So the goal of this work was to provide users with the ability to control a bimanual robot kind of in a way analogously to the way that they would naturally control manipulate the objects in the world with two arms themselves. And we wanted to make robot control in real-world, human-centered environments easier and more effective, even for novice users, for scenarios such as remote home care or telenursing. So before focusing on the robot control aspects of this problem, we first investigated how people instinctively perform bimanual manipulations. So we collected a data set of 12 participants performing numerous bimanual manipulations. And our goal through this process was to extract high-level patterns from this data set that we could in turn use to inform our bimanual robot motion algorithms. And through our analysis, we observed that bimanual manipulations are generally built up from a small set of kinematic actions, which we organize into a bimanual action vocabulary. And these actions are self-handover, one hand fixed, one hand seeking, and fixed offset. So with our bimanual action vocabulary at its core, our shared control method is structured as follows. So the user controls a robot using a mimicry control interface, such that the robot reflects the motions of the user in real time. While the user is controlling the robot, the method uses a recurrent neural network to infer which action from the bimanual action vocabulary is being specified by the user. And the robot engages in appropriate assistance mode to help during the respective bimanual action. So in this example, the user naturally specifies that the robot should pick up the pot with both arms. The method recognizes that the user is specifying a fixed offset action. And the method constrains the robot's motions to ensure that it maintains a fixed translation and rotation offset between its end effectors so it doesn't drop the object. And looking at some examples from our user study. So in this task, the participant is passing plates from the robot's right to left end effector to place the plates into the drying rack on the left. So without assistance, the participant has difficulty performing the task as the distance between the robot's hands does not correspond to the distance between the user's hands. But with our bimanual assistance modes included, the robot adjusts its end effector translation velocities to match hand velocities seen by people when doing self-handovers, and also ensures that its end effectors are the correct distance apart from each other as specified by the user to afford a natural handover or self-handover action. And in this task, the participant is moving the trash bin from one table to the other using both hands. And directly using two robot arms without our assistance modes available makes the task difficult to perform as the arms do not realize that they are coordinated together in order to move a rigid object. So small errors in motion inputs lead to large errors in motion outputs. And with our assistance modes available, the robot realizes that a fixed offset action is present and maintains a fixed translation and rotation offset between its end effectors throughout the action. And using this assistance, the participant successfully completes the task. And a common theme throughout this talk, all of the underlying bimanual motions you're seeing here are calculated in real time using a version of RelaxedIK that incorporates our bimanual assistance modes on the fly. All right, so to briefly talk about where we're going from here. I'd like to motivate our ongoing work by pointing out some of the limitations of RelaxedIK. So first, RelaxedIK is still relatively inaccurate at times. So to be clear, in many cases where the robot is far away from self-collisions and joint position limits, the solver will very easily find very accurate motions with almost like sub-micrometer errors in end effector space. But in challenging cases where the robot is close to collisions or singularities, the solver will add up in millimeters or even a centimeter or more of error in order to avoid these dangerous situations. But I think the question going forward is, can we better avoid these challenging cases such as accuracy, like in general, such that accuracy can consistently be low all the time? And we partially addressed this issue in a paper that we presented at ICRA 2019 with a method called Stampede. And this method creates a smooth and feasible motion on the fly that's guaranteed to be highly accurate in end effector space. However, in order to achieve this extra accuracy and feasibility, we had to frame this as a global pathwise optimization problem, meaning computation speed took a big hit in order to achieve that extra accuracy. So I think a question going forward is, can we have this extra accuracy? Can we avoid these challenging situations while still having this be on the fly in real time? And the second limitation of RelaxedIK is that it cannot avoid collisions with complex environments. So it may be able to avoid big kind of static fixtures, such as a wall that you could bake into the neural network, say if a robot is like always in the same place. But in general, it's not going to be able to avoid complex collisions in complex or cluttered environments or dynamic environments and things of that nature. So we have two ongoing solutions that have really looked at this limitation over the past year. So first we have a method called CollisionIK that is currently under review. And this adds a separate environment collision avoidance objective term within the RelaxedIK optimization structure, while still trying to maintain other objectives as best as possible, such as end-effector pose matching. And all of these motions are still per update, so it still feels and operates like an IK solver in a per instant way. But on the fly, it's doing this collision avoidance with the environment. And here's another example with CollisionIK compared to RelaxedIK and the Move It Cartesian Planner. And we're able to also have different varieties of environment collision avoidance, say just doing position matching or adapting the kind of objectives that you want based on how far the robot is from a collision. So one of the problems with CollisionIK is that it might still be susceptible to local minima. And one way that we're getting around that is we've proposed a new sampling-based motion planner that finds solutions significantly faster than other sampling-based or optimization-based motion planning methods. And we think this is actually fast enough where we can incorporate this into some of our real-time control loops and do many iterations of motion planning and replanning on the fly. And this work is also under review at this time. So wrapping up with a quick discussion. So throughout this talk, I've presented on a number of previous and ongoing research threads for achieving feasible and accurate motion on the fly. And going forward, we have many ideas for how we can take these methods and maybe combine them into a method that truly captures a lot of this space. So we're really excited about where this can all lead to and the many applications that this might open up with these technical methods, such as more shared control stuff in, say, remote home care, telenursing, space robotics, remote surgery, or nuclear materials handling. And just a few kind of overall takeaways from all this. First, perhaps consider approaching research problems in a more end-to-end way, all the way from technical solutions to end-user applications. I personally have found it very fulfilling to work on things at both a low level and then see how these low-level algorithms actually operate in the hands of novice users who have never even seen a robot before. And I think this really gives a good perspective to see how the algorithms that we all work on could potentially, impact real people going forward. And secondly, I kept coming back to this triangle view of my research question. And I think especially for maybe undergrads or newer graduate students who may happen to be watching, consider maybe thinking about the kind of vertices of your research question, so to speak. I think it's a good way to grapple with and reason about the challenges and trade-offs in your space as you try to create impactful findings. So with that, thank you so much, and I'll take any questions. And yeah, thanks.
Okay, let us thank Danielle for the amazing presentation. So thank you very much, Danielle. We will now open the session for questions. So if you have any questions, please raise your arm and you can just unmute yourself and ask, or just put in chat, or send us by private message in the chat as well to any host. Okay. Let's see. Okay. Seems that everyone is a bit shy, so I'll go first. Okay. Daniel, first of all, thank you for the amazing presentation. We talked before about your experience in computer graphics, and I think it clearly shows. This was one of the better looking presentations I've ever seen.
Thanks.
And in the beginning of your presentation, right in the beginning, you talked about what does it mean to be effective? What does it mean for a robot arm motion to be effective? And you talked about feasibility, accuracy, fast computation, right? And you came over and over again to that triangle representation of your goals.
Yeah.
Right? I was thinking more about what if we put a robot in an environment where it needs to interact with a human, because most of the tasks that you have shown here, it seems like the robot is doing his own thing, right?
Yeah.
Maybe when we want to interact with humans, imagine that you have like a robot bartender, right? In the bar, there's a couple of people there and he wants to pour some drinks. Maybe we need something more. We need some sort of intentionality, some sort of legibility of the motion.
Yep.
Can you just give some quick words about what would you think that it would take to employ your system now, considering also this new dimension? So I know it will break your representation, your triangle representation, but with this new dimension, would it be possible to extend your work considering this type of information as well?
For sure, for sure. And I think that's a really interesting point. Actually, some of the first work I did kind of when I stepped in as a grad student in my current lab, it was actually on this whole idea of intent expressive motion and coming up with an optimization framework that could, effectively, show the intentionality of the robot. And this was obviously building on work that had previously come before in this area. And I think we've actually been discussing a lot whether we can take that idea of motion legibility through those kind of optimization frameworks and doing it in a more per instant, per frame kind of way. So could you take a kind of nonlinear, objective function and just, plug it into something that resembles RelaxedIK, and then you just get legibility? I think that's an ongoing thing. But to speak to your more general question of, should the triangle be expanded to include these extra things? I think absolutely. I think I think the three things that I brought up are kind of the primary things that I've been thinking about to afford solutions to this kind of shared control and effective kind of usability problems throughout my PhD. But I absolutely think that there's these kind of other dimensions that have to be considered when a human is nearby. And I think it's a good question to, I even at the end, I hit on this point of like, what are the vertices of this research space? And I think you hit on something really important, that just because you might be focused on one particular part of the space, you shouldn't kind of put your blinders on and forget that, as soon as something, people might be present or other things might be present in the environment, these should definitely be on your radar in terms of, research questions and problems to solve going forward. But yeah. Okay,
thank you very much. I think we all need robot bartenders, so I hope that you expand that in the future. So Rachel has raised her hand. So please, Rachel, go ahead.
Yep. Hey, Daniel. With respect to the bimanual stuff, you mentioned you gathered data, analyzed what people did, and fit it into 4 categories.
Yep.
I'm curious, when you did the evaluation after, if there's any motions that the participants did that didn't fit into those 4 categories, and if so, how the system handled that.
Yeah, that's a good question. So I think, so to first provide more details on the actual analysis we did. So there was something that resembled kind of a PCA kind of factor analysis thing. where essentially, we looked at kind of like the scree plot, and we had to decide kind of where to cut off, when it seemed like, the relevance of these actions weren't kind of relevant anymore. And I think what we found was there were things that didn't kind of squarely fit into these boxes. But when kind of reviewing the exact kind of PCA data next to like videos of this happening, it seemed like it would so rarely come up in like a robot control, context that, not that we swept it under the rug, but we were like, I bet with these 4 things we could make a good prototype system to kind of prove the concept of this. I think one thing right out of the box that our current system wouldn't handle is, any force related thing, because we weren't instrumenting people's hands with, say, like force torque sensors, we're not going to be measuring like torque as people are like, unscrewing the top of a bottle or something. So I think it's worth pointing out that we were looking at, kinematic data, and we were applying this in a kinematic way. So I think if we were to extend this kind of method, I think that's a good way of looking at it, that say, maybe we should add in like a force torque sensor, and maybe, our bimanual action vocabulary kind of expands to say like 8 things that, we might be able to add in these assistance modes. I think what we were going for was not like kind of perfection with the exact labels we had, but kind of something that said, that at least allowed us to kind of bootstrap this kind of shared control method. And we think there's a lot of room to either expand this bimanual action vocabulary, as well as, supplement the assistance modes that could come along with that new action vocabulary.
Thanks.
Thank you so much for your question. We also have a question by Kim. And it asks, can you currently deal with constraints or demonstrations beyond mimicking end-effector trajectories? I'm thinking about applications where the full arm configuration might matter, or in mobile manipulation scenarios. If not, how would you approach this extension?
Sure, yeah, so the first kind of version of mimicry control, we were trying to mimic the whole arm. And our feeling was, well, this has to be important because, let's say a person is reaching into a box, there's a very particular way to do that in order to kind of maybe avoid collisions with the box or things of that nature. I think, at least in our current instantiations of this, because the physiology is so different between the manipulators we've been using and the human arm, it's more important to allow the robot to figure out its own objectives and constraints. Like its self-collision kind of manifold might be so different than the human arm that it doesn't really matter how the human is doing it. Like, just let the robot figure that out. That being said, if you had a very kind of anthropomorphic arm that you really want to be inspired by the whole human arm, there's nothing stopping RelaxedIK from considering, say, like other joint points along the arm. There's nothing special about the end-effector point from RelaxedIK's perspective. You could very easily have, an elbow, position and orientation matching thing, or a shoulder orientation matching objective. And it could also consider all these things on the fly. So maybe you say, I care most about the end-effector position matching and orientation matching. But if you have a little bit more redundancy, also care about these things a little bit too. It'll try to kind of reason and reconcile with all those objectives on the fly. So while we haven't tried this out, not that we haven't had a need, but like I said, our focus has been more on these auxiliary objectives that, say the robot should kind of handle more on its own. But I think using an anthropomorphic arm, there would be ways to incorporate those kind of objectives.
Okay, thank you, Danielle. Any more questions in chat? If you want, you can just raise your arm or write in the chat like Kim. I have several questions. Let me go start with, when you talked about your automatic dynamic camera control, right, that you presented, it looks like from the teleoperation is basically uses motion controllers, right?
Yeah.
That take into account maybe some sort of frame of reference of the human, right? So the human is doing some motion. And when you're taking into account the fact that the camera that the human is observing also is moving, I was going to ask you, what if there was some kind of issues where the person, maybe due to the camera motion, is not really understanding what the robot is doing, if you see some solutions to this problem, and if you ever thought about maybe considering in an extension of this work that also considers other types of camera control. Maybe imagine that, for example, you have an AR or a VR system that allows you to really understand what is the reference frame of the human and allows you to create and to produce that motion.
Absolutely, yeah. Thanks for bringing that up. Actually, one of the so we had 2 user studies in that actual paper. In this talk, I only brought up one of them, so I appreciate being able to talk about the other one. So I think that the whole issue of control frames and reference frames, especially when, you know, having a dynamic camera, I mean, I think that was one of the problems that we thought may have been like a non-starter for this solution, because it seems so difficult for the user to kind of do these mental gymnastics, to do these rotations on the fly in order to even approach you know, this 6 degree of freedom control problem. I think our solution to this was, and I think I alluded to this in the talk, was you know, someone has a motion controller and you always recenter the control frame to how the user is seeing things on screen. So it's always kind of this first person point of view. So like, let's say the camera rotates this way and you want the robot to move away from you. That's always going to be like into the screen. So at least there's some kind of, you know, common denominator that someone can latch onto and say, okay, I at least understand the semantics of these translations and rotations. I won't go as far as to say that maybe this is the best possible way to do it. I think it was just a first thing that we did. We compared it against an absolute control frame, so where, you know, the user would actually have to keep track of how the camera has moved and how to kind of like offset that translation and orientation. And that was totally impossible for anybody who came in to try it to do. So I think our main success was getting the control frame problem and reference frame problem that you talked about to a point that was at least usable by almost everybody who came in and tried it. I still feel like there's a lot to be figured out in terms of the perceptual aspects, the mental rotations aspect of, you know, is there a way that we can, you know, more naturally tap into the way that people naturally see and perceive the world and how we naturally perceive what our control frame is, even as our, you know, head is moving around. You know, maybe so much proprioception is baked into our brain that we truly don't have a way of kind of translating that to a robot control problem. You know, I think these are all open questions. Getting to your second question about AR and VR, I mean, I think that's really interesting. I think as these technologies become more and more available, you know, having these things at our disposal will just allow for more and more immersive interfaces. So I feel like the better you can situate yourself in the remote environment, I gotta imagine the better this whole reference frame problem will be. Either both, you know, egocentrically located, like when you're personally controlling the robot, and also like if you're controlling a robot like around someone in the remote environment, I think having that kind of you know, shared reference frame will be really, really beneficial. So I feel like something to definitely keep an eye on, and something, you know, to keep expanding on.
Okay, thank you so much for the discussion. Unfortunately, it's already time, so we need to wrap up this session. I would just like to take 2 more minutes of all of you, of your time, just to quickly announce the next speaker. So let me just share my screen. Hopefully this works. All right. And so next session is going to be next week with Carl Mueller from the University of Colorado Boulder. Okay, he's going to be talking about robot learning from demonstration, which is a fascinating topic as well. And surprisingly, Carl Mueller, as a fun fact, is a major fan of mountain biking. So if you are also into mountain biking and want to discuss beyond just robot learning from demonstration, please contact the guy. Having said that, I would like to thank Danielle for the amazing presentation and discussion, and all the audience for attending. And I hope that we see each other next week. Don't forget, we have the Slack channel if you want to engage in further discussion with Danielle or just talk with him, and with all the other colleagues that we already have there in the Slack channel, and the Twitter if you want to follow us for the next week's announcements to keep up with these sessions. So thank you very much and see you next week.